here you might want to look back at. Okay, so first we're going to just talk about ordered pairs. And an ordered pair is simply, it's always written like this, with two numbers separated by a comma inside parentheses. By the way, these don't have to be numbers. You know, they could be, two might be the color red, and this three might be male or female or whatever. It doesn't matter what these are. But generally in a college algebra class, it's going to be two numbers separated by a comma. The first number, in this case 2, we generally call the first coordinate of the ordered pair. And in algebra, we usually think of that as the x coordinates. You know, most of the equations we work with have x and y as the variables. So usually we think of that first coordinate as the x coordinate. 3 is the second coordinate. We generally think of that as the y coordinate in an algebra class. There are sort of historical names for the first and second coordinates that really aren't used anymore, but I'm going to go ahead and mention them at least because you might possibly see them in some homework or other at some point. Sometimes the first coordinate of the ordered pair is called the abscissa, and I'm trying to remember how to spell it. The first coordinate is sometimes called the abscissa, and the second coordinate is sometimes called the ordinate. You won't ever hear me use that terminology, and really in the modern day, I don't think you'll hardly ever hear that used. But those are kind of, I guess, historical names for the first and second coordinate, the abscissa and ordinate. But generally, I'll just say the first coordinate or the x coordinate, that would be 2, or I'll say the second coordinate or the y coordinate, and that in this case is 3. So that's what an ordered pair looks like. The reason we call it an ordered pair is because the order matters. In other words, the ordered pair 2, 3 is not the same as the ordered pair 3, 2. Everybody see that? So the order that the numbers are written in matters. And here's why. Well, here's one of many reasons why. We can plot ordered pairs as points in the rectangular coordinate system. So y'all are probably all familiar with this X and Y axis situation. We usually call this sort of a construction where you've got, let me get my hand out of the way, where you've got this x-axis, what I'm calling the x-axis, that's just a number line. Like we don't usually put the arrow down here to show that it goes forever in both directions, but it does. And the same is true for the y-axis. The y-axis is also a number line that goes forever in both directions. And you can see that what makes this the rectangular coordinate system is we've taken these two number lines and we've flipped this y number line up vertically at a right angle to the x-axis. And right here where they cross, where the x and y axes intersect each other, that is at 0 on the x-axis and it's also at 0 on the y-axis. Everybody see that? So like on this x number line, where my finger is, that's 0, and then you would go to the right 1, 2, 3, 4, 5, and so on. Or to the left, it would be -1, -2, -3, and so on. And on the y number line, that's 0, and from there you would go up to 1, 2, 3, 4, and so on, or down from 0 on that y number line to -1, -2, -3, -4, and so on. So we call this the rectangular coordinate system. We used to call it the Cartesian coordinate system. And I'll just mention this because sometimes I still will say the Cartesian coordinate system, or sometimes you'll be in other math classes, they might talk about where they say you're working in Cartesian coordinates. If they say you're working in Cartesian coordinates, it means you're working with ordered pairs of numbers and with this X and Y number line set up like this. It was initially called the Cartesian coordinate system, simply because it was named after the guy that came up with the idea. That was René Descartes, the 17th century French mathematician. But rectangular coordinate system, that's what we call it today, generally. And the first thing we need to know is how to plot ordered pairs as points in the rectangular coordinate system. Again, y'all may already be familiar with this, but if you're not, it's something we definitely need to be able to do. So if I wanted to plot this ordered pair 2,3, if I wanted to plot it as an ordered pair or as a point in the rectangular coordinate system, you always start at 0, 0. By the way, the coordinates of that point, so the point that's right there where the X and Y axes cross, that's 0 on the X number line and it's 0 on the Y number line. So that is the ordered pair. That point represents the ordered pair whose first coordinate is 0 and whose second coordinate is 0. Everybody see that? And that point is often called the origin. The origin. And one of the reasons for that is that's kind of the starting point when we're going to plot other ordered pairs. So like if I wanted to plot this ordered pair 2, 3 as a point in the rectangular coordinate system, I would start here at the origin and I would count 1, 2 units to the right till I get to 2 on this X number line. That's our X coordinate, right? Then from there, I'm going to move my pen until I'm directly across from 3 on the Y number line. So I'm going to go 2 units to the right to get to 2 here. Then I'm going to go up 1, 2, 3 units until I'm directly across from 3, right on this Y number line. And right there is the point that represents the ordered pair 2, 3. Everybody see that? And so if you have a point and you want to figure out, well, what are the coordinates of the ordered pair that's associated with that point, you would just look down, or if it was down here, of course, you'd look up. You just look from there to the x-axis to see what the x coordinate of the point is, and then you look across to the y-axis to see what the y coordinate of the point is. And so, and by the way, you can kind of see, if you think about how I plotted this, where I went to the right and I went up and I went across this, you can sort of see why we might call this the rectangular coordinate system, right? Okay, so that's kind of the first thing we need to know, is how to plot ordered pairs. And so I've got several here for us to work on. Here's Celine. So I've got several ordered pairs here for us to work on, for us to plot. And we're just going to quickly run through and plot these because I want to make sure that you see exactly how this is done. I can see I need to get a sheet of, get something under this because I'm bleeding through from the previous page there. So we're going to plot these ordered pairs. And of course, I haven't labeled the little tick marks here along the axes, but you know, this would be 1, 2, 3, 4, and so on, and going up 1, 2, 3, 4, and so on, and -1, -2, -3, -4, -5, and so on. And here it would be like -1, -2, -3, -4, -5, -6, and so on, right? And you can really, sometimes we scale these, but we don't need to worry about that right now. So, okay. Something real quick. Okay, I was making sure that Paris still's not with us. Okay, so we're going to plot this point 3, 5. So we're going to start at the origin where the X and Y axes meet. We're going to go 3 units to the right till we get to 3 on the X axis. Then we're going to go up 5 units until we're directly across from 5. See, it's right here on the y-axis. So we're going to go over to 3 and then we're going to go up to 5, and right there we're going to plot that point. And so that is the point that represents the ordered pair whose x coordinate is 3 and y coordinate is 5. Everybody with me? Okay, so here we want to plot the point whose x coordinate is -2 and whose y coordinate is 3. So we're going to start at the origin, but we're going to go 2 units to the left till we get to -2 on the x-axis. And then we're going to go up 1, 2, 3 units until we're directly across from 3 on the y-axis. So we go out to -2, up 3 units till so notice we're directly above -2 on the x-axis, and we're directly to the left of 3 on the y-axis. So that point represents the ordered pair to -2, 3. Everybody see that? -1, -4. So I'm going to go from the origin 1 unit to the left till I get to -1. And then do you see I'm going to go down 4 units, right, until I'm directly across from -4. So left 1 and down 4. And that's going to put me right here. And so that's the ordered pair where x is -1 and y is -4. +4, -3. So x is +4, y is -3. So I'm just going to go from the origin 4 units to the right till I get to 4 on the x-axis. And then this says I'm going to go down 3 units till I'm directly across from -3, which is there. Till I'm directly across from -3 on the y-axis. So notice if you look up, you see 4, that's the x-coordinate. If you look across, you see -3, that's the y-coordinate. So that's the point for -3. Everybody with me here? Okay, before we plot these last two, I want to talk just a little bit about these points we've plotted so far. This rectangular coordinate system, the x and y axes, what they do is so a plane, mathematically a plane is a flat two-dimensional surface that goes forever in every direction. So imagine this sheet of paper, except this sheet of paper keeps going forever in all directions. It's just a flat sheet that goes forever. And so you can see that what the x and y axes do is they break the plane up into 4 regions, right? You've got this region above the x-axis and to the right of the y-axis, and above the x-axis and to the left of the y-axis, and below the x-axis and to the left of the y-axis. And then you've got this region to the right of the y-axis and below the x-axis. And so these 4 regions are called quadrants, and we name these quadrants, or we number them, I should probably say. So here we've got quadrant 1, quadrant 2, quadrant 3, and quadrant 4. We always number them exactly like this. We always number them with Roman numerals, and we always number them counterclockwise, starting with the upper right quadrant. Everybody with me? That's universal. It's important that it's universal because we need to be able to talk about the quadrants in a way that mathematicians from any country, anywhere in the world would understand instantly, because the quadrant a point lies in is actually kind of important. And for those of you, if there's anybody in here who's going to be taking any calculus, specifically pre-calculus, before you take calculus, which is mainly trigonometry, there are important things about the quadrants a point is in. So notice, think about it a minute. Do you agree that every single point that's in the first quadrant is going to have both positive x and y coordinates, right? Both the x and y coordinate of any point in quadrant 1 will be positive. In quadrant 2, the x coordinate will always be negative, the y coordinate will be always positive. In quadrant 3, both coordinates will always be negative because you're to the left of 0 on the x-axis and you're to the left or below 0 on the y-axis. And in the 4th quadrant, the x coordinate's always positive and the y coordinate's always negative. And that actually kind of turns out to be important in trigonometry specifically. Okay, so let's look at these last 2 points where we've got 0 as one of the coordinates. So if I wanted to plot this point, the ordered pair where x is 0 and y is 2, I'm going to start here at 0 on the x-axis, and I'm not going to go any units at all left or right. Y'all see that? Because I'm moving 0 units in the, you can always think of x as kind of the horizontal direction and y as the vertical up and down direction. So I'm going to start here at the origin. I'm going to go 0 units left or right. That's 0 on the x-axis. Then I'm going to go up 2 units until I get to 2 on the y-axis. And so that's actually the point where x is 0 and y is 2. Do y'all see that? Do you also see that every single point on the y-axis is going to have 0 for its x-coordinate, right? So like if I just plot this point, I know that that's where x is 0 and y is -4. Everybody see? So every point on the y-axis has 0 for its x-coordinate. That also turns out to be important, as we'll see, particularly in section 3 of chapter 2 in our college algebra course. And then this point -3, 0, that's going to actually be a point on the x-axis. Do y'all see that? Because I'm going to start here at the origin. I'm going to go 3 units to the left till I get to -3 on the x-axis, which is here. Then I'm going to go 0 units up or down, which means I just stop there. Y'all see that? And so that's the point where x is -3 and y is 0. And so one thing to notice, and it's actually an important thing to know, is that every single point on the y-axis has 0 for its x-coordinate, and every single point on the x-axis has 0 for its y-coordinate. Everybody see that? Okay, so that's how we plot points. Pretty easy, right? I suspect y'all probably knew how to do that already, but we just kind of want to make sure we're sort of on the same page as we get rolling here. All right, what's coming up now are a bunch of definitions, and I'm just going to kind of leave it up here a minute. I'm going to talk you through each of them, but then I'll leave it up here a minute in case you need to write these down. So a relation is any set of one or more ordered pairs. So a set that's only got one ordered pair in it is a relation. A set that's got infinitely many ordered pairs in it is a relation. Any set of any number of one or more ordered pairs is called a relation. A function is a specific kind of relation. A function is any relation in which no 2 ordered pairs share the same first coordinate. Now we're going to see some examples in a minute, okay? And we'll talk about how these definitions relate to them. But for now, let's just say a function is any relation, which means a function is any set of one or more ordered pairs in which no 2 ordered pairs have the same first coordinate. And then 2 more definitions here. The domain of a relation is just the set of all the first coordinates of ordered pairs in that set. So let me just go back here where we were plotting these ordered pairs a minute ago. And if I do this, I just drew some little curly brackets around those ordered pairs. And so now that says this is a set of 6 ordered pairs. Y'all see? And so we could look and see, is this set a relation? Yes, it's definitely a relation. I don't even have to think about that because any set that's got one or more ordered pairs is a relation. Is it a function? Well, it's only a function if no 2 different ordered pairs have the same first coordinate. And I actually think all the first coordinates are different, right? 3, -2, -1, 4, 0, and -3. They're all different. So that is a function. We can talk about the domain. You can talk about the domain of any relation. This one happens to be a function, so I will say that the domain of this function is just the set of numbers 3, -2, -1, 4, 0, and -3. Of course, if I wasn't a slob, I would write those in order from smallest to biggest. I probably should, but it doesn't matter because a set is not ordered. In other words, the order you write the members of a set in don't matter. It's still the same set. So that's the domain of that function. Y'all see that? It's just the set of all the first coordinates of all the ordered pairs. And then finally, the range is just the set of all the second coordinates of ordered pairs in that relation, right? So back to our little function here, do you see that the range would just be the set of numbers 5, 3, -4, -3, 2, and 0. Just a set of all the second coordinates, that's the range. Everybody with me? Okay, so we got those definitions. Yeah, I'll just leave those up there a second. Y'all let me know when you've got down whatever you want to get down from that. I thought y'all were young, hip, super technologically superior and so forth. Students that would just take a photograph of that with your phone and move on.
A phone will forget. Paper never forgets.
A function, when you're looking to see if it's a function, it's just the first number of efforts
That is what the definition says, right? We're about to see if y'all have that here in a minute.
So what would it be if there's two?
Yeah, we're gonna look in a minute at some examples to hopefully make it real clear what is and isn't a function and what is important to making it a function and what doesn't matter or has no bearing on it. Okay, we ready? All right. So let's look at some these are just some little simple sets of ordered pairs. So this first one, there are 3 ordered pairs in this set. Is it a function? Remember, we know it's a relation. Any set of 1 or more ordered pairs are relation. Is this relation a function?
Yes.
Yes, because the first coordinates are all different. What is the domain? Just the set of numbers 1, 3, and -5, I agree. And what is the range? Just the set of numbers 2, 4, and 7. Everybody see how that goes? That's super simple, right? How about this second one? Is this a function? No, why is it not? Because those 2 ordered pairs have the same first coordinate. Do you see that? So this is a function. This one is not a function. It's just a relation. We can still talk about the domain and range. What's the domain of this relation? Just 1 and -5. And you don't have to say 1, 1, -5, right? It's either in the domain or it's not. So the domain would just be 1 and -5. And its range, I guess, would just be 2, 4, and 7, right? Is this a function? Yes? Does it matter that these 2 ordered pairs have the same second coordinate? Because that definition of a function it doesn't say anything about second coordinates, right? It's only all the first coordinates have to be different. So it is a function. And the domain would be the set of numbers, well, if I put them in order, -5, 1, and 3. And the range would just be the set of numbers 2 and 7, right? Now this one's a little trickier. This is a relation. It's a set of 1 or more ordered pairs. Is this relation a function? Yes? Everybody agree that yes, it's a function, or anybody think it's not a function? Say again? Technically, it's a function? Does everybody agree with that? No? Because technically is all we care about. This is math, right? It says a function is any relation in which no 2 ordered pairs share the same first coordinate. So I think y'all are right, because here's what do y'all agree that what we have to ask ourselves is this? First, is it a relation? Yes. Everybody agree it's a relation? So a function is any relation in which no 2 ordered pairs share the same first coordinate. So does this relation have 2 ordered pairs that have the same first coordinate? Does this relation have 2 ordered pairs that share the same first coordinate? Then by definition, it is a function. Do y'all agree? I mentioned this one because this one's very confusing for students because they're thinking, well, two ordered pairs can't have the same first coordinate. This doesn't even have two ordered pairs, so it can't be a function. It doesn't say that a function has to have two ordered pairs. What it's saying is it can't have two ordered pairs with the same first coordinate. If it doesn't even have two ordered pairs, it definitely will not have two ordered pairs with the same first coordinate. So the point I'm making is any function, any relation that has only one ordered pair is automatically a function. And of course, the domain is just the number -6 and the range is just the number 13. Now, with that said, we're typically not interested in functions that only have one ordered pair, right? They're super boring. In fact, we're typically not interested in functions with three ordered pairs either. Most of the functions we'll be interested in have infinitely many ordered pairs. And that's why we're going to have to kind of think about what this definition of function means and how we can extend that idea to help us figure out a way to work with functions that maybe have, more ordered pairs than we could actually write down or whatever.
The range on the top one, it's gonna be 2 and 7, right?
2,
No,
4,
the one
and
above.
7.
The one that we just did, the one above.
Oh,
The 2 and 7.
you mean this thing?
No,
This thing?
yeah, no, the bottom one.
This
That
one?
Yeah. The range
Yeah.
is 2, 7.
The domain is 1, 3,
Yeah.
-5. The range is just 2, 7.
Okay.
Everybody with me on this? This is actually pretty easy, right? So far, this is a lot easier than chapter 1. Do y'all agree? I mean, I think by and large for a lot of students it is. Okay, I want to talk a little bit about graphing. Now, y'all's homework doesn't really crank up with the graphing too heavy duty just yet, but it does have some stuff in there where they ask you to do this. I'm going to call this a T-chart, but here we can graph equations, okay? So we know we can plot ordered pairs in the rectangular coordinate system. If we can plot ordered pairs in the rectangular coordinate system, here's the thing we need to know. Every equation has every equation with two variables, which is kind of the big thing we're moving to in chapter 2, or equations that have two variables. Every equation that has two variables, the solution set of the equation is a set of ordered pairs. Probably why we've been talking so much about sets of ordered pairs. So, if you just solve the equation, let's say instead of y equals 2x minus 3, if you did 2x minus 3 equals 7. Well, when you solve that, you're just going to get a number, right? I think you would get x equal 5. We all should be able to solve that by now. Add 3 to each side to get 2x equal 10 and divide each side by 2 to get x equal 5. So the solution to this equation is a number, just one single number. But here, notice that if I plug 5 into this equation for x, do you agree that when I do that, I'm going to have y equals 2 times 5 minus 3, which is 10 minus 3, and so I'll get y equals 7, and that is an ordered pair where x is 5 and y is 7. Y'all see that? And so when you have, everybody with me there? So when you have a two-variable equation, every solution of the equation is not just a number, it's a pair of numbers, right? You've got to tell what the x value is, but when x is 5, there's only one number that you can replace y with that makes that statement true. So if you're going to go with the solution where x is 5, you've got to also tell what the y value is that goes with it. It's going to make it true if you plug those numbers into this equation. Everybody see that? The other thing you can see is, what if I plugged in, what if I replaced x in this equation with -3? What would y turn out to be? -9, I agree. Because all she's doing is plugging -3 in here in place of x and calculating the right-hand side. And it will literally say y equals whatever that is. And 2 times -3 is -6, and -6 minus 3 is -9. So if you plug -3 in for x, you literally get y equal -9. Then that tells me if I replace x with -3 and y with -9, this equation's true. So that's a solution, right? What if x is -1? What's y?
Oh, you plug in to check your word, plug in the numbers the opposite?
I-
Or you're using -3 for x, right?
Well, yeah, here I'm going to use -1 for x.
Yeah.
And when I do, what's y going to be? -5. So everybody see where they're finding that at? They're literally just multiplying 2 times -1 and then doing that minus 3. That's -2 minus 3. Y is -5. What if I plug 0 in for x? What would y be? Say again? -3, I agree. That one should be easy to see because any term that's got x in it is just going to become 0. Y'all see 2 times 0 is 0. 0 minus 3 is -3. It just leaves me with that constant term. What if x is 2? What's y going to be? Yep, I agree. Because 2 times 2 is 4 and 4 minus 3 is 1. We'll do one more. What if x is 4? What's y going to be? 5, I agree. Because if you plug 4 in here for x, 2 times 4 is 8. 8 minus 3 is 5. You get y equals 5. So these are all ordered pairs, and I can plot those. I actually can't quite plot the ordered pair 5, 7 here because my y-axis only goes up to 1, 2, 3, 4, 5, right? But if I had made my y-axis a little taller, I could plot that point. But let's see if we can, and I can't really plot this one either, but maybe I can get down to there. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So -3, -9. So if I go 3 units to the left, there's -3. And if I go down 9 units till I'm across from -9, I could plot that point where x is -3 and y is -9. Or x is -1, y is -5. Well, there's -1 and -1, 2, 3, 4, 5. So somewhere right in there would be where x is -1 and y is -5. If x is 0, y is -3. That point's on the y-axis, right? X is 0, y go down 1, 2, 3. So that's where x is 0, y is -3. That point, by the way, well, let's go ahead and finish graphing, then we'll talk about that point. If x is 2, y is 1. So now I need to go 2 units to the right and up 1. So somewhere right about in there would be where x is 2 and y is 1. And then if x is 4, y is 5. So 1, 2, 3, 4, and up. I think that's 1, 2, 3, 4, 5. Somewhere right in there would be the point where x is 4 and y is 5. Now, something to notice about this, and it's not totally noticeable because my art skills are terrible, but keeping in mind that I've drawn this freehand without graph paper and a straight edge, right? Can you see that all these points look like they don't quite look like it, but they are all on the same line. And by line, I mean straight line. So in other words, if I could just draw a straight line through those points, and again, it's not totally straight, but that's just because I did this freehand. But all these points are on this line. Do y'all see that? It turns out that every ordered pair solution to this equation, y equal 2x minus 3, every ordered pair solution to this equation shows up somewhere as a point on this line. And every point on this line, if you figure out the x and y coordinates that go with it, is going to give you a solution to this equation. Y'all see that? So what we'll say is we have sketched the graph of the equation y equal 2x minus 3. Essentially what we've done is we have drawn a picture of the solution set of this equation, right? Because every point on this line, and there are infinitely many of them, every point on this line would represent a solution to the equation. So for instance, if I plug, let's say I plug -4 into this equation, 2 times -4 is -8, and -8 minus 3 is -11. So -4, -11 is a solution to that equation. I'll bet you if I go out here to -4, and if I go down until I hit the graph, remember this was -9? Sure enough, that'd be -10, -11. That's the point, -4, -11. See that? So every solution to this equation is a point on that line. And every point on this line corresponds to an ordered pair that's a solution to that equation. Everybody see that? By the way, that's why equations like this, notice we only have variables raised to the first power here, right? That's why equations where you only have variables raised to the first power are called linear equations, because the 2-variable version, the graph is always a line, and in math, line always means straight line. Everybody see that? So let's see what we got here. So this is one of the things they do though in the homework, is they'll give you like an equation, and they'll just give you an x coordinate, and they'll ask you to find the y coordinate that goes with it. Everybody see how to do that? Just plug that x value in and find out what the y value is that goes with it. We'll do one more similar one to that, and then we're going to kind of move on to one more idea. And I think, if I'm right, I think that's the last thing really I have to say tonight as far as talking about new stuff. So this is similar to what we just did. We want to graph this equation. Now notice, do y'all agree this one is not linear? That's y equal x to the second power minus 1. I wanted to do one of these that wasn't linear because I want to make sure you see what kind of happens when you start plugging stuff in. I'm just going to pick several x values. You can pick whatever you want. That's actually a good question. So Julia's asking, you can pick whatever you want for x. Yeah, you can, but like I probably wouldn't want to pick 100 for x if I'm trying to graph it, because if I do, I can't show that on my graph, right? Like you got to think about, like you're trying to find ordered pairs that you can actually plot. And by the way, if you did need to pick x equal 100, you could scale your axes where you could say maybe this is like, 20, 40, 60, 80, 100 or something. But we'll try not to do that, unless we need to. And so I'm just going to pick -3, -2, -1, 0, 1, 2, and 3. That's 7 different x values. And if you find all the y values that go with it, that's 7 different ordered pairs that we can plot. And here's the thing to get. Like if y'all just briefly look back at the one we just did, you may have already known that that graph was going to be a line. But if you didn't know that the graph was going to be a line, then you would feel like you needed quite a few points plotted to have some idea what the shape of the graph is. Because you can see what we did. We plotted those points, and then we just basically played the connect the dots game, right? To try to draw a picture of the entire graph. It does and it doesn't. Like now that we think of it this way, now that we know that every single equation where you only have x and y to the first power, now that we know that every single equation like that is going to have a graph that's a line, what's the fewest number of points I could have gotten by with and graphed the thing? 2, I agree. Because do you agree that if I just randomly plot 2 points, how many different lines are there that go through both of these points? Only 1, do y'all agree? 2 points uniquely determine a line. So when we did this, when we graphed this, we hadn't talked about the fact yet that the graph was going to be a line. We didn't really know what the shape of the graph was going to be, so we might have felt like we needed a lot of ordered pairs to figure out, try to get some idea what the shape of the graph is. Now that we know that all the equations that look like this, where you only have x and y to the first power, are going to be lines, we know that really we could have gotten by with just 2 of these ordered pairs, right? But this is not linear. I suspect the shape of the graph won't be a line. So again, even if you do have an idea what this graph is going to look like, let's pretend like we don't, in which case we might want several ordered pairs. Because, you know, what if it's got a bunch of little loops up and down and stuff? And what if we only get a couple of points and we don't have any idea that all that's going on in the graph? So, all right, y'all start plugging and chugging. Just take a minute and see if you can figure out, because this is one of the things you got to be able to do. You got to be able to plug a number in for x and find the y value that goes with it. I'm kind of lost tonight because I didn't bring a cup of coffee, and I'm just kind of like bouncing off the walls. If x is -3, what's y going to be? Say again? Check your signs. Think about what happens when you square a number, when you multiply it times itself. Did you say 8? How about 8? +8. Everybody see that?
Why do you want to put on my calculator?
Because you didn't put -3 squared in your calculator. You put the negative of 3 squared. It should be -3 in parentheses squared.
Okay.
Does that make sense? Because your calculator knows the order of operations. If you don't put parentheses around that -3, it's not treating it as -3 squared. It's treating it as the negative of 3 squared. You need the parentheses around the -3 to force it to negate it first, because otherwise exponentiation comes before that. Does that make sense?
Yeah.
And so if x is -2, then what's y? Say again? 3, I agree. How about if x is -1? 0? I agree. What if x is 0? -1, I agree. What if x is 1? What if x is 2? What if x is 3? Y'all don't see that those numbers are just going to repeat from what you got when you plugged in -1, -2, -3? Because isn't 3 squared the same as -3 squared? Y'all see that? Is everybody able to fill in these y values? So, I'm sorry?
How are you getting the y? Like, what are you?
So let's say that we want to know what y is when x is -3. So I've got y equal x squared minus 1. But my x is -3. So that's what I've got to calculate. Does that make sense? I'm just plugging that x value into the equation in place of x, and then I'm just doing the arithmetic. -3 squared is +9. 9 minus 1 is 8. So I get y equal 8. So if x is -3, the y value goes with it is 8. And I'm just going down the line doing that with each of those x values. Everybody see that? So if x is -3, y is 8. Let's see. If I have 1, 2, 3, 4, 5, 6, 7, 8. Whoa.
There a cow in the other classrooms? That's what it sounds like.
Whoa.
Sound like someone sped off the car.
Sounds like someone drove it. That's in the original.
So there's where x is -3 and y is 8. Everybody with me? When x is -2, y is 3. So there's -2. 1, 2, 3. About right there. X is -2, y is 3. When x is -1, y is 0. Does everybody see that's this point on the x-axis? When x is 0, y is -1. That's this point on the y-axis. Everybody see? When x is 1, y is 0. That's this point on the x-axis. When x is 2, y is 3. That's about here. And when x is 3, y is 8. It's sort of a V. It looks kind of like a V. It's a little more like a U, to be honest. The graph is going to look something like this. And it'll go like that. Something like that. That particular type of graph is called a parabola. A parabola. Or if you're from Far East Texas, maybe parabola. But I'm trying to go with parabola. It turns out that every quadratic function equation where you've got two variables and you've got an x squared in it, the graph will always be some kind of parabola. Everybody with me? So, in fact, give me just a second here and I will show you all this.
Will always be symmetrical?
Yes. It depends on what you mean by symmetrical, but it will always be. We'll talk about that in just a second. So hang on, I'm going to put this up on the screen so you can see it. And let me switch to this because while we're seeing this, the recording won't see it. So let me change what I'm sharing. Tink, tink. Okay. So if I wanted to graph y equal x squared, what was it, minus 1? Minus 1. This will do a little cleaner job than my terrible art skills will do anyway. Try and get some of this stuff out. Okay. So y equal x squared minus 1, and there's that graph. And notice there looks a little more like what we've got. You can see there's that 0, -1, and there's -1, 0, and 1, 0, and there's -2, 3. And if you look straight across, there's 2, 3, and so on. Y'all see that? And it doesn't matter. Like, let's say I did something like this. What if I asked it to graph y equal maybe -2 x squared, maybe plus 3. So -2 x squared, I didn't want plus 3x. I didn't want to get that complicated yet. Hang with me. Delete. Just -2 x squared. Why does it keep doing that? I'm not telling you to do that.
You're clicking out of it while it's on the line.
Plus 3. Yeah, but I got to hit enter. But what if I hit equal? Okay.
I think that's
All right. So -2x squared plus 3. I already told y'all it's got an x squared in it. So it should be a parabola, right? Now that last parabola, remember y'all, look, it was like a U shape. This is going to be a parabola too. What do you think might be a little different about the shape? Any ideas?
rainbow.
A rainbow. Instead of a U, it's a rainbow. Or if you're less imaginative than Chelsea, it'd be like an upside down U. Something like that. Okay, that's a good call. I think that's right.
I'm wrong.
And there it is,
And I'm
right?
right.
No, I mean, I like when my students, kind of like think a little outside the box on it. A rainbow. I wouldn't have thought of that. But y'all see, but it's still a parabola. Y'all see that? So, okay, let's get out of that. Let's go back to our document camera and try to wind this part of it up pretty quick. So, okay. Then we know, here's the thing I wanted to mention though is this. Let me talk just a minute before we move past this. This is about all I've got anyway. Just a couple other little things quickly. But one thing I wanted to mention is what we're talking about graphing here, where we're just using this little T-chart and we're picking a bunch of X values and plugging them in and finding a bunch of Y values, go with them and plotting those points. That's a terrible way to graph, okay? This is kind of our first steps towards seeing what's happening when we're graphing. But we've already seen, for instance, that if all we were trying to do was graph this thing, we wasted a lot of time here, because if we had known in advance that this graph was going to be a line, just like y'all told me, we would have known that we really only needed 2 of these ordered pairs, right? And I'll tell you something else we would have known. If we had thought about the fact, remember when we plugged 0 in for X here? And I remember Selena instantly said, I said, what's going to happen? What do you get if you plug 0 in for X? She instantly said -3. You know why? Because she instantly saw that, look, if you plug 0 in for X, every term that's got X in it's going to be 0. And all it's going to leave is Y equals whatever that constant term is. So actually, if we really knew a little bit more, we would have known when we saw this that we already know one of the points because we know it's going to hit the y-axis at -3. See what I'm saying? And that point, negative, or that y value -3, that is called the y-intercept. That is the y-intercept for the graph. It's where the graph crosses the y-axis, right? And that's always going to be whatever that constant term is, that's always going to be where it hits the y-axis because that's the y value you're going to get if you plug 0 in for X. And just like I said earlier, it's important to know that every single point that has 0 for its X coordinate is going to be a point on the y-axis. So if we had known that, along with the fact that it's going to be a line, we really could have just plotted that point instantly, and we would have only needed to plug one other value in for X and find the Y value, right? Plot that point, draw the line that goes through them. For something like this, we plotted like 7 points. And of course, in doing that, we found out that this graph is a parabola, but we didn't know that beforehand. And in fact, how do we know that if we had picked some bigger X values maybe, how do we know that the graph wouldn't have done something like this? And if we had picked some bigger X values, how do we know that it wouldn't eventually go back and do that? And if it does do that, then this is a terrible picture of the graph. Do y'all agree? So the big point I wanted to make here is what we're doing here is super inefficient. It's also not even guaranteed to give you a reasonably accurate graph because if you don't, before you ever start graphing, if you don't already have some idea what the general shape of the graph is going to be, how do you know when you've plotted enough points? Like I say, how do you know that if we hadn't picked more X values out here, this thing wouldn't have made some weird turn that we totally missed out on? Y'all see what I'm saying? So one of the things we'll be doing in college algebra, kind of a lot of what's left, in fact, involves this idea of graphing by already having, because it turns out there are ways to sort of figure out in general what the shape of the graph is going to be before we ever get started. Everybody with me there? Okay. For now, I don't think the homework that I've got for the 401 class, I don't think it's actually got you drawing graphs. It does have you plugging a value in for X and finding Y. It has you plotting some ordered pairs. But you're going to definitely see this in college algebra. Okay, the last couple things I want to talk about, and then I'm going to stop and we'll take a break. And anybody who wants to work on homework, get questions answered, whatever, I'm here for that. So other ways to think of a function. So here's the way we have so far. A set of ordered pairs where no two of them have the same first coordinate, right? But again, most of the functions we're interested in have infinitely many ordered pairs. Like you can't literally write them all down. So here's what you're going to see. Like here's an equation, kind of like that first one we graphed. I think that one was y equal 2x minus 3. Y equal 2x plus 1. That's an equation. If you remember any of your high school algebra at all, I am certain that you've had an algebra teacher who wrote something like this on the board and said, class, look at this function. And to me, this is right where we begin to get algebra students all confused, because I just talked to you about the fact that a function is a particular kind of set of ordered pairs. And then I say, hey, here's this function. And you're looking at it going, well, that's not a set of ordered pairs, it's an equation. Technically, you're correct. Technically, this is not a function. It is probably more proper to call it a function. Maybe we could call it a function rule or a function definition. This equation is not a function. It defines a particular function. It describes one particular function. The function, y'all listen to this real closely. The function is not the equation. The function is the solution set of the equation. The function that's being detailed here is the set of all the ordered pairs that make this equation true. Everybody see what I'm saying there? So, you know, if I plug 3 in for x here, do y'all agree I'm going to get 7 for y? And if, right, because 2 times 3 is 6 and 6 plus 1 is 7. So if x is 3, y is 7. Everybody with me there? Or if I plug -2 in for x, then I'm going to get what? -3 for y. And if I plug 0 in for x, I'm going to get 1 for y. That's my y-intercept if I were to graph that, right? And so the point is, this equation technically is not a function, but it's a definition of a function. It's kind of like a little map that tells me how to get to any particular ordered pair in this function. Like, for instance, I want to know the ordered pair in the function that this is describing that has 10 as its x coordinate. Well, this tells me how to get there. Oh, the ordered pair that has 10 as its x coordinate is the one that has 21 as its y coordinate. Y'all see that? So y'all will see in college algebra, I will often say, let's take a look at this linear function. I'm well aware that technically the equation's not the function, but really I'm referring to the ordered pairs that are solutions to the equation, right? But it's real common for us to call equations functions when really what's true is the solution set of that equation is really the function we're talking about. This is just a quick way to talk about it without having to list ordered pairs till we die and say this is a little piece of the function, right? Sometimes that equation will not be written that way. It will be written this way. And this is called functional notation. And here's exactly what I mean when I say this. Notice what I've got written here is exactly what I had before, except I've replaced this y with this little weird thing, f with x in the parentheses. Everybody see that? Usually I read this f of x. I'll say f of x is equal to 2x plus 1. That is kind of shorthand for saying f is a function of the variable x. But f of x and y are interchangeable. If you can figure this part out and get this to make sense to you, this whole functional notation thing is going to be a lot easier for you to cope with. It's very simple. But what you've got to realize is f of x and y are the same thing. It's two different ways of saying the same thing. So f of x really kind of accomplishes two purposes. First, it gives a specific name to this function. Like I'm going to say this is now, I'm going to call this the function f. And you can see why we use the letter f, just because generically it's the first letter of the word function. But you know, what if I was working with two different functions within the same problem? And maybe I've got one of those is y equal 2x plus 1, and maybe the other one is y equals 3x minus 2. Well, it would be a lot easier if instead of writing my functions like y equal 2x plus 1 and y equal 3x plus 2, if I said that this one is f of x equal 2x plus 1, and maybe g of x equals 3x minus 2. And so what I've done is I've given a specific name to each of these functions. And that way, if we're working with both of these within the framework of the same problem, if I want you to look at this one, I don't have to say, okay, now look at the one that says y equals 2x plus 1. Oh, and then look at this other one that says y equal 3x minus 2. Instead of being so verbose, I can just say, look at f, and then look at g. And you know exactly which one I'm talking about each time, right? So one reason we do it is just because it gives a specific name that helps us identify which function we're talking about. In business math, a big thing you deal with is revenue cost, and profit. And so instead of having, maybe y equals 2x plus 1 is my cost function and y equal 3x minus 2 is my revenue function, we would call this one C of x and this one R of x or something like that. And then if you've got a separate profit function, you might call it P of x for profit. It just makes it easy for people looking at the problem to sort of stay straight. The other thing this functional notation does is this. If I use this functional notation, f of x equals 2x plus 1, or maybe I don't use it and I use y equal 2x plus 1. So if I wanted you to evaluate this function when x is 5, then I would have to say something. If I'm using the y notation, I would have to say something like, find the value of y if x is equal to 5 or something like that. Here, all I have to do is write this. That's it. This tells you everything you're being asked to do. What is this asking me to do? Replace this x with 5 and figure out what that's equal to. Do y'all agree? See, if I did that here, I would have to say, find y if x is equal to 5. Find the value of y if you plug 5 in place of x or something like that. Here I can literally just write f of 5. And here's why it should make sense to y'all that that's what it's telling you to do. Remember, we got that little rule that says anytime you have an equation, other than things like multiplying or dividing both sides by 0, you can do anything you want to one side of the equation, but whatever you do, you have to do the same thing to the other side. Do y'all agree? Okay, well, look at this equation. Now look here. I just changed something on the left side of this equation. I made a change, which is on the left side of that equation, I replaced x with 5. Well, if I replace x with 5 on the left-hand side of the equation, do you agree that what that's telling me to do is the same thing on the other side? In other words, replace that x with 5. And of course, then we just do what we do, which is that literally tells me to multiply 2 times 5 and add 1. And so I get f of 5 equal 11. Y'all see?
Will it ever say f inside the parentheses 5, what is it called, comma 6, comma 1, comma whatever? Like if you like the same thing as over here where you the same thing that you said. Well, let's do the x is 5. Oh, let's do.
Oh, where you got like the little T-chart with a bunch of x values. Yeah, it might tell you to, here's how it would probably say that. So y'all, I want to say just a little more about this, but let me answer her question right quick. I think that it would do it something like this. If it was going to do what she's asked. So here's what she's saying. She said, you know how I've had that little T-chart where I had all those x values and I wanted you to plug them all in and find all the y values? They would probably do something like this. So f of x equals, I don't know, 3x plus 1 or whatever. And it would say something like, find f of x if x equals whatever, -2, -1, 0, 1, 2, 3. It might say something like that.
Oh, so it won't actually put it in parentheses with the x?
I mean, it could write find f of -2, find f of -1. I don't think it would say find f of -2. Like, I don't think it would say find f of, you're saying, would it ever do this? Like that.
Yeah.
I'm not going to say that I've never seen that before because I'm certain I have. I don't think it's super common to do that. I don't think they'll do it here, but if you did see that, that would be what they're telling you to do, right? Is just go through each one of these in turn, find f of -2, then find f of -1, and then so on, right? Don't think they would ask it in that sort of style, but if they did, that is what they'd be asking. But see, here's the thing, the other thing I wanted you to learn, to see here, and then I got one other little thing and we're done talking for the night at least, is first of all, notice that f of x when I say it's the same thing as y, yes. When in this equation, where I've got it written like this with the y, if x is 5, do you agree that y is 11? Well, in this equation, when x was 5, f of 5 was 11. That's literally the value of y when x is 5. Do y'all see that? And so what the other thing that's kind of nice about, or one thing you need to see about this functional notation is, when you find that f of 5 is 11, do you agree that what that's telling you is, remember, because what is 5? Oh yeah, that's the value we plugged in for x. That's clearly an x coordinate, right? Well, what is 11? Remember, we replaced y with f of x, and that f of whatever turned out to be 11. Clearly, that must be the y coordinate. Do y'all see that? So when you see f of 5 equal 11, that's telling you that the ordered pair where x is 5 has y is 11, and that's the ordered pair that works in that function, right?
So we wouldn't leave our answer as 5, f.
If all they asked you to do is evaluate f of 5, evaluate just means see what f of 5 is equal to, then you would plug it in, you would get 11, and that's the answer you would give. But I would want you to see that what that means is the ordered pair where x is 5 and y is 11 is one of the ordered pairs in that function. Everybody with me? Okay, last thing. So we're talking about other ways we can think of functions besides just as this set of ordered pairs where the first coordinates are different. So sometimes we'll use an equation that we think of as a function because it defines a set of ordered pairs that is actually a function. And then the other way would be, besides equations, would be graphs. So a lot of times we'll have a graph maybe like this, and I might say, take a look at this function. Well, it's not a function, it's a graph. But this graph is made up of infinitely many points. Each of those points has an ordered pair associated with it, and the set of all those ordered pairs, that's actually the function. Y'all see that? And so like this looks like the ordered pair here where x is 0 and y is 1. And maybe that's the ordered pair where x is 1 and y is 3. And see, all of these points on this graph are ordered pairs, and all those ordered pairs together make up the function. By the way, be careful about this because students will see this and they'll go, oh, this is the function that has 0, 1, 1, 3, and I guess that one's where x is -1, y is -1, and this is where maybe looks like x is -2 and y is -3. So like I'll ask students, what's the domain of this function? And they'll say -2, -1, 0, and 1. That's wrong. That's a little tiny piece of the domain. You're just giving me the x values of the ordered pairs that I labeled, right? But everybody look at my pen. There's an ordered pair there, right? That's a point on the graph. There's an ordered pair there. Maybe that's where x is 1/2 and y is 2 or something like that, right? Well, that would be an ordered pair in that function. So we're not too awfully worried about that right now, but it is something we need to think about. This entire line is a bunch of infinitely small, infinitely packed together points, right? And when I say that, what I mean is if I pick 2 points on this line and it looks like they're bumping right up against each other, there are actually infinitely many points on that line between those 2 points, right? Like if we had an electron microscope and we could zoom in close enough or whatever. So that's why we need graphs and equations, because literally we could never list all those ordered pairs, right? But we can come up with something that lets us sort of visually see a ballpark of what each of those ordered pairs might be, or an equation where we could literally figure out, okay, well, I don't know all the ordered pairs, but whichever ordered pair you want me to know, just tell me the x value you're interested in, and I'll find the ordered pair that has that x value, by plugging it in and getting the y that goes with it. Everybody see that?
So what is the domain then?
The domain of this I think would be all real numbers, from negative infinity to positive infinity, every real number. Because think about this.
Oh, so we only have domains when we do the equation, but not on the graph?
No, it's got a domain.
Yeah, it's gonna have domains, yeah, but we're not.
It's got a domain. We're just asking what is the domain? It's every real
Yeah.
number, right? I mean, the domain of this, wherever this was, the domain of this is every real number as well. Because do you agree that no matter what number you pick in the universe, you can multiply 3 times that number and add 1, and you're going to get some other number in the universe? Although that first number that you plugged in and that number you got as your answer, those are both in the domain and range, right?
So
This is in all real numbers too.
will we get asked to find a domain?
Oh,
on the
yes.
graph?
Definitely you
Can we
will.
choose any-
Definitely you will. And that's something we're going to spend some time going over in the college algebra part, is how to look at the graph and figure out what is the domain, what is the range. But for that particular graph, the domain and range are both going to be all real numbers for sure. Okay, that is all I've got. We're going to take a break. I'm going to take 10 and come back in here. Let me hit record. I'm going to turn off the